one of these protocol is multiple granularity protocol. This protocol is among like-based protocols. Okay, like-based. Protocol. I do not teach this protocol, but I say something about it. In multiple granularity protocol, which is among like-based protocols, likes are taken in on data item which has different granularity. For example, if we consider data items, it may be a record or a row of table. Okay, it may be a table, it may be a set of tables, it may be the whole database. So we have different granularity for data item. We have a small data item which is record or a row of a table, or a bigger which is a table, or more bigger which is a set of tables, and at the end we may have whole database as a data item, and we can put when we can take logs on these data items. We can take log on record, we can take log on table, we can take log on a set of tables, or we can take a log on the whole of the database. So we may take logs in different levels of data. We may have on record a table, a set of tables, or database. Sometimes it's better we take logs on records when we are working with record and we are working on the level of records. It's better to take logs on records, because if we take log on, for example, whole database, but we are going to just work with a record, this prevents other transaction to work with database, because if a transaction like the whole of database, then the other transaction cannot work
جزاك الله خير
with
عشير.
database. So if you are working on the level of record, or on the level of rows of tables, we can just take logs on records. But if you are working in a higher level, for example, if you are going to read all the records of a database, it's better to get or to take a log on the whole database. Uh, Otherwise, we should go and like every records which may many number of records, and it's not good to take a lock on every record, uh, and we read all the database. So it's better to take only one lock on the database and read the all records of database. So we may take locks on different levels of, of, of data items. Uh, it's a protocol that we do not go in details of it. We skip it. I think we can go forward and teach other topics of the next chapters. So we do not teach this protocol here. I just want I just want to introduce you this protocol, and you hear the name of the protocol, multiple granularity protocol. There is another there is another there is another there is other protocols which are called multi-version multi-version protocols. Uh, okay. In timestamp ordering, uh, as you see, um, when a transaction wants to read a data item or wants to write a data item, first DBMS first checks the timestamps. If a transaction with a bigger timestamp has read data item or has write data item before we are going to read or write, we should or operation is rejected, and we should roll back, and we are late. We can solve this problem by considering multi versions for any data item. A data item, for example, a data item Q, data
Item.
item Q may have many versions: Q1, Q2, Q3, and so on. So we have some versions for data item for data items. Consider these are versions of data item Q, Q1, Q2, Q3, and QK. Uh, when a transaction modify data item Q, it creates a new version of Q. And when a transaction wants to read Q, it goes and finds the proper version of Q and read that version. Okay. Uh, by multi-version in multi-version protocols, read operation is always successful, and read operation uh, does not is not rejected, and always is successful. So multi-version protocols are introduced to improve the performance of timestamp ordering protocols by considering versions for data items. Uh, Read operation is always successful, and the number of rollbacks of transaction is decreased, and the performance is increased. This is a, this is a total this is a total description or an overview of Multi-version protocols, again, I do not go in details, and I prefer to skip this protocol. Okay, I want to talk about uh, deadlock handling, which is a topic of this chapter. So these two last protocols, we skip these two last protocols, and we go for talking about deadlock handling. Deadlock handling.
Deadlock handling.
Okay. Um, you know what is deadlock? Um, if a transaction is waiting for another transaction, a transaction is waiting for another transaction to free a lock, and that transaction is wait for another transaction, and these waitings make a cycle. Then we have deadlock. Okay, this is the wait for graph. Wait for graph. Wait for graph is a graph whose nodes are transactions. Nodes are transactions, and age we have an age from Ti to Tj. If Ti waits for Tj to free a lock, a lock. Okay. Mm, if we use lock-based protocols, in lock-based protocols, we may have deadlock. In lock-based protocols, we may have deadlock. Okay. Uh, um, Deadlock is not good because transaction which are in a deadlock waits forever, and cannot proceed, cannot uh, cannot do their work, and they are waiting forever. So deadlock is not a good situation. We should prevent uh, deadlocks. For handling deadlock, there are two approaches. Handling deadlock. We may prevent from deadlock, or we may allow deadlock occurs and then resolve it. So can prevent deadlock, or we can allow deadlock occurs, and then we detect
Excuse me, doctor, your voice is gone.
What's the problem?
Your voice gone.
Oh, okay. Let me check. Hello. 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 Merci. Yes. Voice?
Yes, doctor. Yes.
Yes, now it's okay. doctor.
Sorry, there was a problem.
Yes,
Sorry.
doctor. Yes.
Okay. خب. Let me continue. So for deadlock handling, we can have two approach. In the first approach, we can prevent from deadlocks, and deadlocks do not occur at all. In the second approach, we can allow deadlocks to occur, but we can detect deadlocks and we can recover from deadlock. These are two approaches that we can handle deadlocks.
Prevent, detect, recovery.
Okay, detect and recover. We can detect that there is a deadlock, then we can recover the deadlock. Let me talk about the first approach, preventing from deadlock or deadlock prevention.
السلام عليكم دكتور.
سلام
السلام
علیکم.
عليكم.
سلامت باشید.
Please, Doctor, I will ask about deadlock. You say he's delayed because he's
Yes.
waiting.
Yes.
Just that's this problem because he's waiting. He's
Forever.
waiting. Is that is delayed? Correct?
Yes.
Deadlock.
Transaction, when transaction are in a deadlock, okay, transaction is waiting. Because there is a cycle, this waiting does not finish at all, and forever a transaction is waiting, or it is always in waiting state. Okay, it is not a good situation because transaction cannot do anything and it is waiting forever. Okay, Ti is waiting for TJ is waiting for TK is waiting for Ti. So all of them are waiting, and they cannot continue. They cannot proceed.
It's looking like stacking, not just waiting. Stacking forever,
Stack?
right? Yeah, stack, not just waiting forever. I mean,
Yes, waiting for others. Yes. Uh, uh, Ti is wait for TJ. Okay, TJ is wait for TK is wait for Ti. If there is not a cycle, if there is not a cycle, then deadlock, then we do not have deadlock. Uh, Deadlock is equal to cycle in a wait for graph. Deadlock is equal to a cycle in wait for graph. So we have deadlock if and only if there is a cycle in wait for graph.
Okay, that's clear. Thank you very much.
So what we can do, we can follow two approaches. The first approach, we can prevent from deadlock. We can we do not allow deadlock occurs. Okay. When deadlock occurs, when a transaction is wait for others, and the other is wait for the first transaction. If we have only two transactions, for example, wait for TI, wait for TJ, and TJ wait for TI. Okay, and a cycle is formed. If we do not allow one of these edges is formed, then this cycle does not form, and we do not have deadlock. This cycle is formed because we have an edge from TI to TJ, and another edge from TJ to TI. If only we have one of these edges, then we do not have a cycle. So we can prevent deadlock by do not allowing one of these edges. Suppose timestamp TI. Suppose TI has a timestamp and TJ has a timestamp. Suppose timestamp TI is less than timestamp TJ. Okay. Please note that deadlock handling occurs in like-based protocols, not timestamp-based protocols. Okay, so timestamp that we use here is only for deadlock handling, not for concurrency control. For concurrency control, we can use like-based protocol or timestamp-based protocol. Suppose we are use like-based protocol. In like-based protocol, because of waiting, maybe a deadlock occurs. To prevent deadlock, we can use timestamp just for handling deadlocks, not for concurrency. These transaction use likes and are using a like-based protocol. But suppose also transaction has timestamp. The timestamp TI is less than timestamp TJ. We use timestamps only for handling deadlocks. Okay. Okay. I said that a cycle is formed if we have an edge from TI, an edge from TI to TJ, and another edge from TJ to TI. If we prevent one of these edges, then we do not have a cycle and we do not have a deadlock. So we may allow TI wait for TJ. Excuse me. TI waits for TJ, but we do not allow TJ wait for TI. Or we may allow TJ can wait for TI,
But you may not.
but we do not allow TJ wait for TJ. In every case, we do not have a cycle and deadlock does not occur. In the first case, TS, which has less timestamp, is older transaction. Okay, older younger. Transaction that has less timestamp is older and has come sooner to the system. And transaction that has a bigger timestamp is younger and has come later. So in the first case, in second case, in the first case, older waits for younger, but younger cannot wait for older. In the second case, younger can wait for older, but older cannot wait for younger. Okay. Based off these two cases, we have two approaches. These approaches are
الأولى أكون
named are called wait, die, and wound, wait. The first approach is wait, die. The second approach is wound, wait. Okay. In the first approach, wait, die, we do in this manner. When TI requests a data item currently held by TJ. TI is allowed to wait. TI is allowed to wait if timestamp TI is less than timestamp TJ. Suppose timestamp TI is less than timestamp TJ. So if TI wants or requests a data item currently held by TJ, TI is allowed to wait if timestamp TI is less than timestamp TJ. Otherwise, if TJ requests a data item currently held by TI, TJ is rollbacked. Excuse me, let me correct it. Rolled back. Die in this die in the name of this approach means rollbacked. Okay, you have wait or rollback. You have wait, die. The older transaction waits for younger transaction. The older transaction waits for younger transaction. But if younger transaction wants or requests a data item that currently held by older transaction, then younger transaction cannot wait and should be rolled back. Should be rolled back, and excuse me, should be die. So older transaction wait for younger transaction, but younger transaction does not wait and rolled back. In the second approach, which is called wound wait, when
wouldn't wait.
TI, which is older transaction, when TI requests data item currently held by TJ, which is younger transaction, then TJ is rolled back, which is called wound. When in the second approach, when the data item is held by younger and older transaction wants data item, then younger should be rolled back. Younger is wound, and younger transaction is rolled back. If TJ, which is younger, requests a data item currently held by TI, which is older, then TJ is allowed to wait. Okay. In brief, if I want to explain on the picture, in the left side we have wait die approach. In the right side we have wound wait. In wait die approach, if older transaction which has less timestamp wants a data item that is in hands of younger transaction, then older transaction is wait for younger transaction. If younger transaction wants a data item that is in hands of older transaction, then younger transaction cannot wait, is not allowed to wait, and should be rolled back and should be die. In the second approach, which is called wound wait, if an older transaction wants a data item that is in hands of younger transaction, then then older transaction forces the younger transaction to be rolled back, and the younger transaction is wound, is forced to be rolled back. On the other hand, if younger transaction wants a data item that is in hands of older transaction, younger transaction is allowed to wait. Okay. Is there any question?
Doctor, how can decide which one it must be wait
Uh,
or which one it's need to be die?
um, we either run wound weight approach or weight die. We use one of these approaches, okay? Or either we use weight die or we use wound weight, okay? If we use weight die, the older transaction waits, and the younger transaction, uh, when younger transaction wants the data item, then it is rollbacked. Okay. If we use a wound weight approach, then when older transaction wants a data item, then the younger transaction is forced to be rollbacked. If younger transaction wants a data item of older one, then it should be wait. So it depends on which of these two approach is used. If we use weight die, we do in this manner. If we use wound weight, we do it in that manner.
Thank you so much.
Welcome. Okay, deadlock prevention. This is deadlock prevention approach. Okay, these two approach are in the category of deadlock prevention. The other approach is we allow deadlock occurs, then we detect and resolve it, recover it. In deadlock prevention approach, deadlock does not form, is not formed, um, because we do not allow a cycle is formed in the wait for graph. So deadlock does not occur at all. But in the second approach, we allow deadlocks occurs, and then we detect it and recover it. Second approach, uh, detecting deadlocks and recovering. Um okay, how we can detect and how we can recover. Detecting is easy. We can use wait for graph. We use wait for graph. Okay. In wait for graph, if there is a cycle, then we have a deadlock. Cycle is equal to deadlock. Cycle in uh, wait for graph means that we have a deadlock. So DBMS maintain wait for graph when a transaction requests a lock. If the lock can be granted, then the transaction is successful and takes the lock. But if the request of transaction cannot be granted by DBMS, then transaction should wait for a transaction that already have the lock, already has the lock. So transaction should wait for some transaction that has previously take the lock. And in the wait for graph, an age is formed. For example, suppose we have this schedule TI, TJ. Suppose TJ takes like X on, for example, A. Then TI comes and requests like X on A. Here, this cannot be granted and should be wait because TJ has the like and it has not released the like. So TI wait for TJ. TI waits for TJ. And an age from TI to TJ is formed in the wait for graph. Then, for example, maybe another transaction TK. Suppose TK has taken like X on B. Then in the following, suppose TJ request like X on B, then it should be wait for TK and wait for TK, waits for TK, and so TJ, there is an age from TJ to TK. And suppose in the following, suppose here that TI before executing like XA takes a like on, for example, C. Okay, here. So TI has like on C. Suppose in the following TK request like X and C, then TK waits for TI, and we have a deadlock at this moment because TI has like on C, TJ has like on A, then TI wants a like on A and it cannot take the like because the like is in hands of TJ, so TI waits for TJ. Then TK has a like on B. In the following, TJ wants a like on B and it cannot take the like and should wait for TK. And in the following, TK wants a like on C and it cannot take the like because the like on C is in hands of TI. So TK waits for TI, and at this time a cycle is formed, and so we have deadlock. Is three transaction is waiting forever and cannot proceed. TI is wait for TJ, TJ is wait for TK, and TK is wait for TI. And all of these transactions are waiting for the others and cannot proceed. So they wait forever. Okay. When this situation occurs, in the wait for graph, a cycle is formed. So we can use a simple algorithm, for example, DFS algorithm, depth first search algorithm.
حلو.
Depth
صح.
first search or DFS algorithm. By using excuse me, by using DFS algorithm, we can detect cycles. By using depth first search algorithm, we can detect cycles. So when we detect a cycle in wait for graph, then we know that there is a deadlock. A deadlock has been occurred. Okay? Is it okay? Any question?
Yes, Doctor. Please, can you explain this table again?
This table is in a Z schedule. Okay, it is a schedule. Uh, in this schedule, suppose Ti first takes a lock on C. Okay,
Okay.
it's okay. It's successful. Then Tj comes and takes a lock on A, and it is also successful. Then after that, suppose Ti wants a lock X on A. This request cannot be uh, granted because previously TJ has the lock on A, and Ti should wait for TJ. Okay, Ti should wait for TJ. So in the wait for graph, an edge is formed from Ti to TJ. Then suppose in the following, TK comes and takes a log X and B. Okay, it is successful. Like X and B is given to TK. Then after that, suppose TJ wants a log X and B. This uh, cannot be given to TJ because at the moment TK has the log X and B. So TJ should wait for TK.
Okay.
Okay.
Mm.
Then in the following, suppose here when TJ waits for TK, an edge is formed from TJ to TK.
Okay.
The previous edge was from TI to TJ. The second one is from TJ to TK. Then suppose TK continue and wants a like on C. We cannot give the like X on C to TK because previously uh, we had
As looked.
we uh, give we give we give the like and C to TI. So here TK cannot take the like and C, and it should be wait for TI. So TK is waiting for TI, and an edge is formed here from TK to TI. Then in the wait for graph, a cycle is formed, and we can detect this cycle by DFS algorithm.
Mm.
You know DFS algorithm, okay?
Okay, Doctor. Thank you so much.
Excuse me,
So
doctor.
yes, please.
In the previous approach, we use a weight die or wind weight to solve the problem. What can I do now? Just only detect the deadlock only, or there's some way to solve this problem?
Yes, in the previous approach, deadlock does not occur at all because we prevent forming, we prevent deadlocks, okay? No cycle is formed and we do not have any deadlock. In the second approach, deadlock can occur, okay? Can occur. Here we have a deadlock, okay? No, the second question is how we can solve, how we can recover. At this time, we detect that there is a cycle. We detect that a deadlock has occurred. But what we should do? What's the solution? What we can do? After we detect there is a deadlock, we should resolve the problem. We should recover the deadlock. What can we do for recovering the deadlock? One of these transactions that are in deadlock, for example, TI, TJ, or TK, one of these transactions should be rolled back. Okay, to recover from deadlock, we select a transaction which is in deadlock, and we select the transaction which is in deadlock, and we rolled back, and we roll back it. This is the solution. We can select one of transactions and roll back. When we roll back the one of these transactions, we undo all the things that it has been done, it has done, and release all the locks of it. We unlock the locks that the lock of the transaction that is selected for roll back. So we can select one of these transactions, for example, TI, TJ, or TK, and roll back it and release its lock. For example, if we select TI, TI is waiting for A, for locking A, and he has lock on C. We roll back TI, and we release the lock X on C by TI. By releasing this lock, here TK can continue and can take the lock and continue its work. So the solution is that we select one of the transactions that are in the deadlock and roll back it. Any question?
Excuse me, is there any rules to select one of them, or a free? Select a free one, TI or TJ or TK.
Do you mean which one we select? Which one is better to we select?
Yes, sir, exactly. Thank you.
Okay. Yes, it's a good question. What transaction should be select? Which one is better for selecting for rollback?
According to DFS, right?
No.
No, DFS just finds.
Solve the cycle.
Yes, DFS just finds the cycle. Okay.
Mm.
For breaking the cycle, we should select one of these transaction and roll back it. But the question is which one? Which transaction is selected for rollbacking? Okay, it's good. It's a good question. When we roll back a transaction, we undo all the work that it has done. So one option, maybe we select the transaction that has done little works. For example, suppose transaction TI has done 2 operations, transaction TJ has done 100 operations. Okay, if we roll back TJ, we should undo 100 of operations. But if we roll back TI, we just need to undo 2 operations. So it's better we select a transaction that has done little operations. Okay, this is one option. Also, maybe there are some parameters. For example, suppose a cycle is formed here. Ti is wait for Tj. Tj is wait for Tk. Tk is wait for Ti. We may have another cycle, for example, here. Okay, Tj, for example, T R T S. If we have 2 cycles and Tj is the common node between these 2 cycles, it's better we select Tj for rollback. Because by rolling back TJ, 2 deadlock are resolved. 2 deadlock are recovered. Okay, because TJ is common between 2 cycles. So there may be many parameters for selecting a transaction for rollbacking and recovering a deadlock. One parameter may be the number of operations that the transaction has done. For example, if Ti has done 2 operations, Tj has done 100 operations, so it's better to roll back Ti because it has done little operations. This is one parameter. The other parameter may be if there are transactions that are common between 2 deadlocks, then we select them to resolve both deadlocks at the same time. So there are many operations. There are many options. Okay.
Okay, Doctor, thank you.
Yes. Okay, let me continue.
Please excuse me, doctor.
Yes, please.
Here we have 2 cycles, right?
We may have 2 cycles, yes, at the
Yes.
same time.
So if we use the DFS, then we'll not have a cycle. So maybe it will be from TK to TJ, to TI to TJ, then to TR, then to TS. So from TJ to TK and from TJ to TS, it will not be hold. So is that not solving the issue in this case?
If we run DFS, okay, if we run DFS on this graph, DFS finds that there are 2 cycles because, for example, we start DFS from TI, we go, for example, to TJ, then to TR, then to TS, then to TJ. So we visit TJ twice, so we find there is a cycle. We find cycle 2 here. Then when we continue and go from TJ to TK and from TK to TI again, we visit TI twice. So we find that there is another cycle. So cycle 1 is found. So DFS can find many cycles, and can find all the cycles in the graph. So we have we have found two cycles. We can know what if there is any node which is common between cycles or not. If there is a node which is in cycle 1 also in cycle 2, so if we roll back this transaction, both cycles are opened, and we have two deadlocks here. A deadlock between TI, TJ, TK, TI, another deadlock between TJ, TR, TS, TJ. By rollbacking TJ, both deadlocks are recovered. If we, for example, select TI for rollbacking TI just open cycle 1 and just resolve the first deadlock, and the other deadlock are also here and are not recovered. So either we should select two transactions, for example, TI for opening cycle 1 and the TR for opening cycle 2, or we can select only one transaction TJ for opening both cycles. DFS can detect all the cycles and can detect which nodes are common between cycles. Then we can select a node that is common between cycles to recover more deadlocks at the same time by just rollbacking one transaction. Okay, any question? Okay, in the following in the chapter, in this chapter, uh, the the simple model that we have for banking, we have a banking system, and we defined two operations. We define two operations, read and write. Read and write. We have, or we had two operations in our model, only read and write. But in the reality, in the practical systems, we may have also insert and delete operations to other consider two other operations. Insert and delete. Okay. Insert operation adds a data item that is not in the database. So insert adds a new data item to database and initializes its initial value, or initializes its value. Delete operation remove a data item from database. The previous operations that we had were read and write. Read reads the value of data item that has already that has already their existing on on database, and also write an existing data item. But insert and delete are different. Insert adds a new data item to database. Delete removes a data item from database. In the reality and in practical DBMS, we have 4 operations. We have all of these 4 operations: read, write, insert, and delete. Okay, so we add the new operations insert and delete to our model. We consider 2 other operations and add them to our model. Okay, let me define insert and delete q. Insert q inserts or adds a new data item q into database and assigns q and assigns q an initial value delete q deletes data item q from database, from DB. Okay, by adding these 2 new operations, we should modify our protocols. We had like-based protocols and timestamp ordering protocols for concurrency. In like-based protocol, we had like X and like S. For reading, for read, we just take and we use like S. For read and write, we use like X. But what about insert and delete? For insert and delete, we should define some likes, and we should say what we should do and what types of like we should take for insert. We should take for insert and delete. Also, in timestamp ordering, we had 2 rules: one rule for reading, one rule for writing. No, we have 2 other operations, so we should have one rule for inserting, one rule for deleting. So we should modify the protocols for these new operations. First of all, we should check compatibility and conflict of insert and delete operation with the other operations. We know that read is compatible with read. There is no conflict between read and read. But there is a conflict between read and write. And also there is a conflict between write and write. But what about insert and delete? Uh, if insert and delete have conflict with the other operation or not, we should talk about conflicting of these operations. So let me show conflicting of these operations in a table. Suppose we have transaction I and transaction J. Transaction I has operation OI and transaction J has operation OJ. And here we show conflict. If transaction OI is suppose it is insert Q, and OJ is read Q. We are going to see if there is a conflict between insert Q or read Q, between insert Q and read Q or not. As we said before, if the order of execution does not matter, and it is not and if it is not important which operation is executed first and which operation is executed second, so there is no conflict. But if it is important, if the order is important and it is important that what operation is executed first and what operation is executed second, then that operations have conflict. So for insert Q and read Q, please see if the order of execution is important or not. For example, if insert Q is executed first, then read Q, the result is the same when read Q is executed first and then insert Q or not. Can you answer my question?
Excuse me, Doctor. Yes, there's a conflict when read X and operate J, read Q. It's conflict when before insert Q,
Okay.
after Q. There's a conflict in this situation.
Okay. Consider two cases. Suppose at first Q does not exist in the database. Suppose we do not have Q in database. Okay.
Doctor, please.
Here suppose Q does not exist in
QI.
database at first. By this assumption,
In this case, it's not important because it's another operation. So it will not make any conflict.
if Q does not exist in database at first, okay. If we read Q, okay, if we execute read operation, and this cannot be done, and we get a logical error. If we read or write a data item Q that that there is not
Finish.
on DB, then we get a logical error. Okay, we get a logical error and operation cannot be done, and the transaction
Conflict.
is failed and should be rolled back. Okay, so if Q does not exist on database at first, if we execute read operation first, this operation gets a logical error, okay, and cannot be done, and transaction TJ is rollbacked. But if we first execute insert Q, execute the operation of insert Q, it is executed successfully and Q is added to database. Then if we execute read operation, it will be successful and Q is read successfully. Okay, so I ask my question again. The order of execution of these two operations is important or not?
Yes, doctor, it is important.
It is
The first
important.
Yes,
process
doctor,
is
it's
important.
very important.
Yes, it is important because if we do insert, then read, everything is okay. The Q is inserted and then Q is read. But if we first execute read operation, there is no Q on the database to be read. So we get a logical error. So the order of execution is important, and it does matter which one is executed first. Because the order of execution is important, so we say this operation has conflict. Read Q has conflict with insert Q because the order of execution of
Not done.
these two operations are important. Okay. Also, insert Q and write Q. Again, the order of execution is important because if Q does not exist, we cannot write Q. Write Q writes on an existing data item Q. If data item Q does not exist on the database, you cannot write on Q because there is no Q, and we get a logical error. Write Q does not add Q to database. It writes the value of Q. The Q should be previously there. So an insert operation should be done before write Q. So the order of execution of write Q and insert Q again is important, and these two operation has conflict. What about insert Q and
Delete.
insert Q?
هنا نفس الريد
Uh,
نفس الشيء. Right.
That can happen.
No. هم conflict أيضا because insert the same
Conflict.
right.
suppose
Insert mean right. Right, conflict.
It's important, doctor,
why why it is important.
because two transaction.
Same transaction. How we can put it there? Maybe it will be a conflict.
Yes,
Uh,
yes. same transaction and other transaction.
Let me check. Okay, suppose again Q does not exist in database at first. If insert Q of TI is executed successfully, Q is added to database. Then when we execute the insert operation of TJ, because in the previous operation Q has added to database, the second operation is not successful because try to add a data item Q to database, but Q is there before. We cannot add we cannot add a data item to database if that data item has already there. Okay, so we get a logical error. So TJ gets a logical error. But if we execute insert operation of TJ first, okay, TJ adds Q to database. Then when TI comes and wants to execute insert Q, TI gets a logical error. So the order of execution is important because if TI is executed first, it is successful, and then TJ is executed second, it is unsuccessful and gets logical error. If we change the order, if we first run, if first execute insert operation of TJ is successful, and when TI comes and tries to uh, execute insert Q, it gets a logical error. So in the first order, TI is successful, TJ gets logical error. In the second order, TJ is successful and TI gets logical error. So the order of execution is important because it determines which transaction be successful and which transaction be rollbacked. So the order of execution is important. So we have conflict. Did you get the point? Is it clear?
Yes, doctor, it's clear.
Yes, doctor, it's clear.
Okay. Now consider delete Q and excuse me. We here check insert Q with the others operation. So here we have insert Q. In the second line, second column, we have delete Q. Here we are going to check insert Q with the other operations. In the left side, we have just insert Q. In the right side, we have read, write, insert, and delete. So we are going to check insert Q with delete operation, insert Q operation with delete operation. And we are going to check if the order of execution is important or not.
Yes,
It is
doctor,
not
it's also important.
It's
Important
important.
because
Yes.
we
Yes,
cannot
yes,
Yes,
we
doctor.
cannot make two operation out
because
in the
different
same item.
operation.
no, because it will
Doctor, it's
delete the
important.
operation. It will not affect another one, right?
Yes. Again, suppose Q does not exist in the database. Okay. If we first execute insert Q, it is successfully added to the database. Okay, because Q is not in the database at first. When we execute insert Q first, Q is added successfully to database. Then we run, then we execute delete Q. Okay, this operation successfully deletes Q from database. Both transactions are successful. But if we do in vice versa, in the reverse order, Q does not exist in the database. If we first execute delete Q, we cannot delete queue from database because there is no queue in the database. We suppose queue does not exist in the database at first. So delete queue cannot be executed and gets a logical error. And the second operation, insert queue, will be successful and queue has added to the database. So if we change the order of execution in the first order, when we insert queue first and delete queue second, everything is okay. But in the vice versa, in the reverse order, if we execute delete queue first and insert queue second, the first operation cannot be executed. Delete queue cannot be executed as the first operation because there is no queue to be deleted, and we get a logical error and TJ is rollback. So it is important in what order we execute these two operations. So the order is important and we have a conflict. Okay, in brief, we see that insert operation has conflict with all the operations, with read, with write, with insert, with delete. So insert operation has conflict with read queue, write queue, insert queue, delete queue. Also, if we check delete operation, it has also conflict with all the other operations. Suppose OI is delete queue. We have delete queue and we want to check with the other operations. Delete queue. Delete queue. Suppose here we have read queue, write queue, insert queue, and delete queue. Here, suppose queue is in database at first. Here, suppose we have queue on database. Suppose queue is in DB at first. Okay. Let me consider the order of execution of delete and read. If queue is in database, if we read queue first, we read it successfully. Then when we delete queue, it will be again successfully, and queue is deleted successfully. But if first we delete queue from database, then we try to execute read queue, read queue gets logical error because there is no queue, and queue is deleted by the first operation, and the second operation gets a logical error. So the order of execution is important, and we have conflict here. Okay. If there is a situation, if there is a scenario, if there is a there is a state in which the order of execution is important, we say that these operations have conflict. Okay, for delete and write, again, the order of execution is important because if we delete queue first and
Yes.
when we try to write, there is no queue to be to be written, so we get logical error, and the order is important. For delete and insert, suppose queue is in database. Queue there exists in database. Okay. If we delete queue, it is okay. It is deleted from database. Then we insert queue. It is okay, and a new queue is inserted in database. But if we do in vice versa and in reverse order, Q is in database at
No
first.
problem.
If we
You
try
is
to insert Q, we cannot
No
be
problem.
successful because
no,
Q is
no.
there, and we try to insert again Q to database, and we get logical error. If we execute insert first, we get logical error. So the order again is important, and we have conflict. What about delete and delete? Okay, Q is in database at first.
امسح
Okay,
شيء امسح عمق.
the first delete is successful. The second delete gets logical error. Okay, so it is important which one is executed first and which one is executed second. If ti delete Q, it is successful. Then tj comes and try to delete Q. It gets logical error because before it Q is deleted from database, has been deleted from database. So the second operation gets logical error. So tj gets logical error. But if tj first execute delete, it is successful, and then if ti wants to delete Q, ti gets logical error. So it is important what operation is executed first and what operation is executed second. In one situation, ti is successful, tj gets logical error. In other situation, tj is successful and ti gets logical error. So it is important which one is executed first and which one is executed second. So again, the order of execution is important, and delete has conflict with delete. So in brief, you see that delete operation has conflict with all the other operation, with read, with write, with insert, with delete. Okay, the time is finished at this time. We finish the session and we continue the topic in the next session. Uh, we we know that insert operation and delete operation have conflict with all the other operations, and we should say how we can modify, how we can change the previous protocols to support insert and delete operations. In like-based protocol, we should say which like operation we should use for delete and insert. In timestamp ordering protocols, we should say what rules we should have for inserting and for deleting. We will talk about this topic in the next session. Okay, if there is any question, please ask me. Okay, no question?
No question, doctor. Thank you
No
Good.
so much.
question, doctor.
Thank you,
No
doctor.
question,
Have a
doctor.
nice day.
Okay,
Thank you, doctor.
No question. Thank you, doctor.
the first of the next session, this chapter has been this chapter will be finished, and we can start the next chapter, which is about recovery. Okay, this chapter was about concurrency control. The next chapter is about recovery. I uh, I omitted some topics. I want to short the content of the class, so I removed and I deleted some topics in this chapter. For example, I did not teach multiple granularity protocols. I did not teach multi-version.
Thank you, doctor. Thank you.
Okay, some topics are removed to make it simple for you to read the uh, content.
Thank you, Doctor, for support.
introducing this topic.
Okay.
Thank you, Doctor.
Have a nice time.
Thank you, Doctor.
Thank you,
Thank you, Doctor.
Have a good time, Doctor. Have a good time.
خدا حفظتكم يا دكتور.
خدا حافظكم خدا نقدر.
خدا حافظ شما.
ثانك يو دكتور.
خدا حافظ دكتور. شكرا.
خدا حافظ. خدا حافظ.
في امان الله دكتور.
في امان الله.
Thank you, Doctor.
شبتون بخير دكتور.
ممنون.
Thank you, Doctor.
ممنون. جمعه خوبی داشته باشید انشاءالله.
ان شاء الله.
ان شاء الله.
میلاد رضا هم تبریک میگم بهتون. مبارک باشه میلاد امام رضا.